I was. All right. Yeah. Every time you can see that. That's fine. You just can just see it for Zoom. Yeah. This is fine. Yeah. Okay. Good morning. I just wanted to make sure that folks in the Zoom can hear us properly. Can one of you just raise your hands or something?
We can hear you, Sagara.
Wonderful. Thank you, Bani. Okay, so good morning. I think we wouldn't have a better day to do this, and I would like to start off this whole session this morning that Tom is going to guide us through. But before that, as like the usual ritual, as his advisor, it's my pleasure to introduce Thomas Varner, to all of you for his PhD defense. Now, before I start introducing him, just I will take a few minutes for the folks that are on the Zoom first and then in the room. So I like to convey every one of you, thank you so much for coming by, who can visit, today physically in this room and also through the Zoom. It has been a really a great journey for all of us, and I will just be very brief in the story for Tom. So a few of the folks that I can introduce from the Zoom are Masa, one of our faculty members from our department, Alan Dutton, a previous faculty member from our department, Alan Whittington, our faculty member from our department, Alison Witch from environmental science, Ananya Mukhopadhyay from all the way from India, one of our collaborators that Tom has worked on, Dr. Bayani Cardenas from UT Austin, who is actually a true part of this particular project that Tom has worked on. And then I think Tom's mom and dad are both here too on the Zoom, so welcome. Professor Ganga Hettiarachchi from Kansas State University, where Tom stopped for a little bit of time for doing some of his experiments. And then we have Harshad Kulkarni, whom I will describe in a minute. He is all the way from India, IIT Mandi. Dr. Hatim Sharif, who is actually a committee member for Tom. I will introduce him to Dr. Janet Ford, a faculty member from our department. And I cannot miss Dr. Kark Nordstrom from all the way from Colorado, Denver. He's an USGS person and very well known to the field where Tom is actually working on. Dr. Laura Richards, all the way from David Pollier's group and from University of Manchester. She's a faculty member and has been quite a bit of an organic geochemistry champion through the years, and probably was one of the reviewers of Tom's paper very recently. So after that, we have Will from UT Austin. If I have missed somebody, please let me know. I think one of Yan Zhang's, Professor Yan Zhang from China, her postdoc has also joined. So thank you, everyone. And now my turn for the room. I'd like to introduce Dr. Steve Goodbread from Vanderbilt University to the right of me. He's one of the committee members, and he's one of the experts in the field for sedimentary geochemistry in the Bengal Basin for a long period of time for his work there. We have Dr. Hongji Zhai from our faculty group, who is also a committee member for Tom's PhD. We have Dr. Heather Shipley, who is the interim provost for our university, and she will be joining a little later, but I just want to acknowledge that she will be coming up very soon for Tom's defense. We have Yongli Gao, our faculty member from our department. And then we have Professor Kaushik Mitra, a new hire for our planetary science group in our department. So welcome, everybody. And I cannot, I have to say, one of my very close friends, Peter Knappett, all the way from College Station from Texas A&M, has driven all the way from there to actually be a part of and won his PhD student and our PhD student for the group, like Tom. So welcome, Peter and Juan, to the group. And then we have Alex Godet, one of our faculty members, Professor Brian Lobb, one of the environmental science faculty members, and all the students. So thank you again for being here. Just a very quick outline of how Tom progressed out here. So 2019 fall, Tom started his PhD journey. He came with a Bachelor of Science degree from the Department of Geology and Geological Engineering from Ole Miss. He taught me that yesterday, University of Mississippi. And then he started his PhD at UTSA. But how it happened was, it's a funny journey, because when this proposal was funded, that was championed by Peter Knappett, Bayani Cardenas, and myself, I was actually at Kansas State employed. Kansas State didn't know that I was going to leave in a few months. with this new grant. And when I left Kansas State, I got the full grant to be operated from UTSA from the month of August. Tom was awarded the Fulbright Award in 2022 when he was also a part of the Fulbright work that he did in India and Bangladesh, along with one who was also funded through the Kwasi. And at the time, they joined with Ananya Mukhopadhyay in India and Harshad Kulkarni. Several newsworthy articles were written on Tom's and this NSF research, and they were applauded by NSF multiple times, actually. You might have seen some of Tom's publications and his presentations at various GSA and AGU and Goldschmidt and Arsenic Congress and so on. Now, where is the next step? He will tell you about the next step at maybe the last slide, but Tom is supposedly, after his passing his defense today, once he gets his degree, he will be off to Houston working for Exxon from the summer. So that's where Tom is heading to. I have to stop for just a second and introduce one person for Tom's defense. It's Harshad Kulkarni. Harshad was a postdoctoral fellow here, and then he became a lecturer. And to be honest, I do claim that I'm Tom's mentor, but I really did zero. It was actually Harshad and Tom played the role of mentor and mentee to guide through the PhD work. All the organic geochemistry work that Tom will present today was basically because of the initiative of Dr. Kulkarni, who is now an assistant professor in IIT Mandi. So with all due respect to everyone in the audience and who are in this room, I'm really thankful that you all came, enjoy Tom's defense. We will have a discussion session after that. And then after that, it will be a closed door for committee members to meet and decide on Tom's fate. And then we will let him know what the decision is. So without further ado, it's Tom Varner from UTSA. Thank you.
All right, hello everybody. So I've been introduced along with a lot of other people. So thank you to everybody who made it. And I'd like to start off by saying there's a lot of people I should thank who helped me along the way, but I don't have time for that. So I'll try to move through this as quickly as possible. So yeah, the title of this is Biogeochemical Controls on Arsenic Mobility within Hyporheic Zone Sediments, which kind of came about because of various studies along multiple rivers in India and Bangladesh, and the end commonality was kind of looking at what these sediments are doing to control arsenic fate within these riverbanks. So really briefly, this is just kind of an outline of the dissertation that I plan to submit. Each of these is a research chapter, except for the first and final, which is the introduction. Yeah. Okay. Oh, I see it. That good? Okay. So anyway, I'll try to move through these as quickly as possible. I think it was a challenge to distill it all down, but hopefully I get the essence across to kind of give this narrative of the research and also the journey along the way, because there were a lot of things that had to change due to the travel bans from COVID closures. And so I think we came through this well. And ultimately, I think I was left with more questions than answers through this PhD. So I think there's plenty of room to move forward. But for now, I'll give a brief introduction on kind of the research proposal and the project and kind of where that led from the start. See, so this is the chapter 1 introduction and a little bit of background on arsenic in the environment. So it occurs naturally, mostly with sulfide minerals and iron minerals. So it's classified as a chalcophile element. And this map kind of shows the distribution of arsenic throughout the world, with the shaded areas being these kind of young fluvial basins. And in the small corner near India, you have that Bengal Basin, which is shaded due to the Cenozoic sediment origins on the map. And so a lot of times it's believed that along mountain ranges, we have the dissolution of these young geogenic rocks with arsenic-bearing minerals, which become eroded and transported down to these basins where it's released into the groundwater. And one of the major areas this occurs is along the Himalayan foreland basin. So all these rivers draining the Himalayas are draining these young rocks with all these sulfide minerals, which are oxidized and subsequently co-precipitated on iron oxides, where then they are transported down to these basins. And so on the bottom here, we have India and West Bengal, where the x-axis on the top here, sorry for people on Zoom or that maybe can't see the pointer that I'm using in the room. Yeah, well, maybe it's not working too well anyway, but on the x-axis on those graphs on the bottom, those are the concentrations of arsenic on a logarithmic scale, whereas the y-axis is depth. And so you can see, at least in India, West Bengal state, and in Bangladesh, the Bengal Basin together, you have a wide distribution of arsenic concentrations, both with depth and distance across the basin. So a little bit of background on the Bengal Basin, kind of the history of it. It is an actively subsiding basin, which means that it is prone to being infilled by sediments. Together, the Ganges, Brahmaputra, and Meghna River make up the world's largest delta. And this has been mostly filled in throughout the Holocene due to the sea level rise and backfilling of the basin. So you have these rivers draining the basin, and over time it got filled in over these interfluves and paleo channels. It's what we see today, which is a massive alluvial basin with these ginormous rivers, huge sediment load just flowing through and depositing all sorts of sands and silts. And so a little bit background on the construction with these rivers. There's a topographic break shown by that white line on this figure that kind of differentiates between the energy of the rivers, whereas on the upside or the north side of this, you have these braided rivers that are depositing a lot of sands, and they're really active meandering rivers. Whereas below that, you get some tidal influence, and these are a bit slower rivers depositing silts and overbank deposits typically. And so on the right figure, there's these kind of the panel B at the bottom, you see this, what looks like a zigzag, like a jigsaw. And that is because this is, say, a cross section of an area where this river deposited sands and then it eventually meanders away, depositing finer grained sediments, but then reoccupation deposits more sands. Of course, in the lower energy areas, you get this interbedding of silts and clays along with these channel sands to form kind of a largely heterogeneous architecture throughout this aquifer, which kind of complicates the groundwater flow patterns and those processes which are mobilizing arsenic. But there are some similarities based on these depositional patterns and what controls the groundwater flow, but also the sediment size. And if you remember that topographic break image, this image here is kind of a percentage of water wells with contamination of arsenic. I'm assuming about 50 ppb, which is the safe limit in Bangladesh. And this is kind of matching up well with that topographic break. So once we kind of get into these lower lying deltaic regions, not such high energy with sands, then we get this release of arsenic into the groundwater. And that's on the large scale. But on the right-hand figure, there's a smaller scale, and we have higher arsenic in black and lower arsenic with the white symbols. And those kind of correspond also to these higher energy and lower energy depositional areas of this previous river. So what's left from those depositional patterns. So we see that these grain size and these deposition, these morphological units do have a control on arsenic distribution. But what releases arsenic in the aquifer is kind of this redox processes. So typically when we are exposed to oxygen, iron is in its oxic state as a solid, and that can immobilize arsenic where arsenic gets sequestered on its surface. Now this iron oxide at our surface is easily reduced under these standard conditions. And so if conditions become reducing, that iron 3 dissolves to iron 2, which is in the aqueous phase. And typically it's believed that this organic matter generates these reducing conditions, kind of driving that dissolution of iron 3 to iron 2. And so what happens then if there's arsenic attached on this iron mineral, in the presence of labile organic matter, that iron mineral can become reduced and that arsenic is released to the groundwater, which is then labeled to be drawn up and used for drinking water purposes. And that's kind of the idea of what is propagating these high arsenic concentrations in the groundwater. Now, this is kind of where the original NSF project I got hired on for, this is kind of where it comes together. So along these rivers, which are, either because of wet season, dry season, or tidally fluctuating, it was presumed that these tidal propagations or changes in the seasonality of the river stage would drive oxalic-rich river water into the riverbank, which would precipitate iron oxides since it brings in the oxygen. Now, when the groundwater is discharging or the river level goes down, then we have the reducing groundwater rich in iron, which comes up and meets with that oxic river water and precipitates iron oxides, which can then sequester arsenic. And so kind of understand this process, we could extrapolate it across the Bengal Basin and other similar alluvial basins and kind of understand better where we can predict these low arsenic concentrations in the groundwater, practice better riverbank filtration practices, and overall just understand the regional cycling of arsenic on a larger scale much better. And so this is what we initially set out to do. And our first trip was in January 2020, right before COVID, and we had planned multiple trips back. And so under that assumption, this is where we established work from my first chapter, which is trying to establish one of these NRVs along the Meghna River. So a little bit of background on the site. Here's the site map in our samples, but the Meghna River was an ideal place to study this because of nearby well-studied areas, Ari Hazar, Mount Lab. They all have high arsenic concentrations in the groundwater. Previous studies have shown arsenic enrichment in the sediments along the riverbank. And it's a tidally fluctuating river that, on the daily tides, if you stand on the riverbank, you can see the river actually come up about 20 to 30, 40 meters pretty quickly within a few hours. And so these circles on the map are the stretch along the riverbank where we collected the sediment cores, which were collected using a probe, so pristine, undisturbed sediment cores, which alongside our colleagues from Texas A&M had a series of piezometer nests to measure the groundwater properties adjacent to these cores. And the squares are monitoring wells, which we drilled using the reverse circulation method, common practice in the villages, and those got us sediments from within the aquifer down to a basal clay layer. And so a little bit of putting it all together to show this off the bat, we have a simplified site lithology where we have riverbank sands, a silt layer underneath the riverbank, aquifer sands, and then a clay aquitard. And so some of our other colleagues, including Juan from Texas A&M, discovered the flow paths, and our colleagues from University of Texas Austin made an ERT transect, which I think this is a good way to kind of sum up the site before moving forward. And so we have this groundwater discharging from the aquifer into the river, but also that silt layer kind of acts as a hydrologic barrier, so we have a separate flow path throughout the riverbank. And so for the experiment we did, we were wanting to establish the kind of baseline differences between these riverbank aquifer sediments, kind of describe what's going on in the riverbank. So we did bulk analyses, including XRF, grain size, and then we also did a 24 incubation with DI water to kind of simulate, what is the effect of infiltrating river water, for example, on these sediments. And from there, we did DOC organic analyses, cations, measured elements using ICP-MS, and looked at some of the DOM spectroscopy, so absorbance fluorescence properties of at least the chromophores in the DOM. So on the left is the solid phase total abundances measured by XRF. And so I thought this distribution was really interesting. So there's an intertidal zone described by Berube et al., so our previous colleagues who worked at the site, a nearby site, who described an intertidal zone, and they similarly found this iron enrichment at the edge of the intertidal zone. And so we have typically high iron ranging between 29 and 53 grams per kilogram, but we have pretty low arsenic. We were expecting to find, if this were like a functioning NRB, perhaps we were expecting to find hundreds or more milligrams per kilogram of arsenic. But yet, I thought we still saw an interesting distribution of these solid phase iron and arsenic. And additionally, I didn't have space to show it here, all the other redox elements kind of behaved similarly between these two. So there was a zone, kind of this intertidal mixing zone, where it seemed like arsenic was more or less being sequestered. And then on the bottom right, we have the dissolved concentrations measured by Juan in Texas A&M, where arsenic and iron were increasing towards the river. And so this is almost the opposite of what we were expecting, where we expected, say, a natural reactive barrier, this NRB, to sequester the arsenic closer to the river. And so this left us with some more questions to explain. And really briefly, these are plots of some of the parameters on the left-hand side of the sediment and on the right-hand side of the water extracts. I just wanted to show the differences between the sediment and the water extracts. For example, in the sediments, the iron, arsenic, the total organic carbon measured by LOI, they were similar in the aquifer sands and the riverbank sands. So not much of a difference in bulk elements concentrations, but they were completely different once we looked at the water extracts. For example, the WEOM in the description, that stands for water extractable organic matter. But this is when we started to realize there is a thorough difference between these two sample types. which could be due to many reasons, including riverbank flushing. But another way to kind of visualize the differences are, on the top hand, these are just PCA plots of partitioning of the solid phase properties, where we have the red, the blue, and the green, which indicate medium sands, fine sands, and clay, respectively. And then the circles are riverbank samples and the squares are aquifer samples. And so the bulk sediments were more or less partitioned on redox and grain size, whereas the water extractable constituents were based on sample type, so aquifer versus riverbank. And this is, I think, an interesting plot to show. This is typically, especially this plot B, these are ion comparison plots. This plot B is usually used to show groundwater types. However, these are sediment extracts. But what I think is interesting here is that the aquifer and riverbank had very separate so-called groundwater types. So in this DI experiment where we leached these sediments with water, we had very different behavior. So divalent cations were much more prominent in the riverbank, which create electrostatic conditions that favor arsenic absorption, whereas in the aquifer, we had high concentrations of sodium, which was surprising to me. But along with that, they correlated almost perfectly with the concentrations of water extractable organic matter. And so sodium and water extractable organic matter together can create a lot of competitive desorption processes, maintaining arsenic in solution. And so looking at the water extractable organic matter properties a little closer, there were large differences between the riverbank and aquifer, primarily in the amounts of organic matter that was extracted. So the aquifer had about 1,200 milligrams per kilogram on average, and the riverbank had only 100 milligrams per kilogram. Also, the aquifer extracts were much more humidified in general, and the riverbank extracts had a very low humidification index, but quite high freshness index and a high protein signature. So in general, those riverbank sands were pretty strong protein-like peaks, indicating more labile organic matter, whereas the silt and clays appeared to be very strongly humic-like, and the aquifer sands were kind of a mix between with a stronger humic-like content. And one of the telling differences as well is the molecular weight of these samples. All the aquifer samples, the silt, the clay, and the sands had about 1.5 to 1.8 kilodaltons or daltons, whereas the riverbank had about, on average, 100 daltons in molecular weight. So a large difference between those two. Keeping in mind, this is just the water extractable organic matter. So this is typically what's going to come off most easily, or the most bioavailable portion of it. And so kind of putting these together, after this initial study, we kind of had a little bit better understanding of the processes, but still were kind of perplexed because the silt layer seemed to be having somewhat of an interaction, and there seemed to be differences in this organic matter that may be driving these processes here. So in the aquifer, we concluded that there was kind of competitive desorption, dissociation of, maybe salts or something contributing to these sodium levels, kind of keeping the organic matter in solution, assuming that there's also humic-like substances which can participate in electron settling or even complexation with iron and arsenic, forming complexes or ternary complexes between the three. Whereas in the riverbank, there seemed to be some accumulation of arsenic in the riverbank, but yet there was still that increase of the dissolved concentrations towards the river, and there was the presence of this labile organic matter. So those ideas kind of set up one of the future studies looking more at organic matter, but this next chapter kind of wants to focus on the mineralogical associations between arsenic and iron. And this one, I think, kind of came about out of curiosity, but there's kind of a well-known idea that low arsenic groundwaters are associated with these orange kind of oxidized sands, whereas like high arsenic groundwaters are associated more with reducing gray sands. And so we know that color has been used as an indicator to associate these safe aquifer types. And initially, we're going to look at heating it to remove the organic matter, heating these sediments, and trying to look at the difference to help identify organic matter more. But what we found was a little bit different, because the heating of sediments and clay minerals specifically induces diagnostic changes, specifically with diffuse reflectance and other spectroscopic techniques. And so there's a whole bunch of papers from relevant fields of archaeology, ceramic studies, looking at these, even brick studies, looking at all these changes in the spectroscopic properties of clay minerals and iron oxides. And so identified a good point to heat these sediments at was 600, which a lot of clay minerals, you could have diagnosed changes at that point, but also the organic matter would have been removed. And so we analyzed before and after using FTIR and diffuse reflectance to kind of identify iron oxides, whereas FTIR is pretty well suited for clay minerals because of the sensitivity to those OH and O bonds, usually like silicate network. The silicate networks are so common in clay minerals. So briefly, this is on the top. These are representative samples from each of the lithologies. So the green is the clay, the blues, the riverbank sand, yellows, the silts underneath the riverbank, and the dashed purple is the aquifer sands. And so the pure sediments on the top, which weren't treated yet, had pretty diagnostic peaks that are similar with clay minerals. And so primarily, it seemed that these were kaolinite, oolite, and a little bit lesser amounts of, say, muscovite chlorite. It's hard to distinguish in such a heterogeneous mixture, but it was clear that those were the most predominant classes of minerals in the sediments, whereas after heating, those peaks decreased substantially and were more similar to the sands. And so to kind of test that, the conclusions that we got from the FTIR, the CIA, Chemical Index of Alteration, kind of looks at the kaolinite weathering series. And so when we plotted along the kaolinite weathering series, the retention of potassium, the sediments kind of indicated more of a trend towards kaolinite, illite predominantly too. And so these samples, they're very young. If we assume they're eroded from the Himalayas and then deposited, those are young rocks, rapid erosion and transportation. So kind of a younger sediments, but they're still relatively moderately weathered because probably the humidity and just the intensity of that process. But the Pleistocene outcrops in the Bengal Basin, I found a paper comparing those. And for example, the CIA of those, which kind of shows the weathering towards kaolinite, so these older, more weathered sediments, they had a CIA of 93%, so a little bit higher than what we saw in the aquifer and riverbank samples along the Meghna River. And so looking at the diffuse reflectance, the top one is just the spectra of the reflectance. So typically, when you see these kind of curved, more parabolic looking curves, that indicates higher presence of iron oxides, whereas the flatter they are, the more gray, the less, I guess, color they would have. So kind of the flat spectra. And in this example, the sands are on the left and the clays and silts are on the right. And we have the solid, which is following the thermal treatment. Whereas on the bottom, we have the delta R. So that's the first transformed derivative of the diffuse reflectance spectra. And that's what's commonly used, especially at the 520 wavelengths, as an indicator of iron oxides in general. But looking a little bit further, you see some peaks that correlate with goethite and ferrihydrite, as well as hematite. So in the sands, we had the presence of goethite in the initial sediments, but after heating, that all transformed to hematite. So we had the oxidation of these iron minerals directly from goethite to hematite, so causing a more crystalline structure. Whereas in the silts and clay, there was minimal presence of goethite, if any, and then a lot of that was transformed to a hematite peak. And so there's a lot of structural iron too that following the dehydroxylation of like kaolinite or illite minerals will actually be liberated or freed up to oxidize. And so we had a lot of that iron in these iron-rich clay and silt being oxidized to hematite. And so at this point, this may kind of seem self-apparent because the grain size correlates with the content of clay minerals. But when you compare this change in delta R at 520, the proxy for iron 3, and compare that to, say, grain size at the lower end, which is the D10, the CIA, the chemical index of alteration, which of course is the kaolinite weather series, and then the initial arsenic content, there's a good correlation for all these. And so one of the things I noticed by doing this too, the prior and post heating of the sediments, was that the arsenic concentrations actually decreased in the sands by about 25%, but in the silts and clay samples by almost 50%. And so I didn't focus on this too much, but I found it interesting that maybe the arsenic was being volatilized. And there's a lot of studies looking at the arsenic from lignite and other coals. So we do know it starts to volatilize at 500 on, but I found that interesting. And so perhaps an indication that this arsenic is associated with organic matter, which is released, or perhaps the certain bonding arrangements of the clay minerals. And so kind of to summarize this, a nice little graphic. kind of showing on the top the measured color and the change after heating. And then on the bottom, those are actually the grain size. So you can see there's the changes. And in general, there was a large change in the silts and clays, much less, if any, in the sand samples, which could be due just to minimal shifting, but pretty negligible amounts of change. So that's more that goethite, which is still iron 3, being transformed into hematite, whereas in the clay and silt, you have deformation of many clay minerals, which leads to the iron oxidation and perhaps removal of, the organic matter in the clays. And so that kind of brings us to chapter 4, and this is the organic specific chapter that I think the second chapter that I presented initially, that one kind of led us to these hypotheses that this chapter kind of tests more thoroughly. And so to do this, we took some of the same samples from each of the lithologies, and we wanted to extract the bulk sedimentary organic matter, which is SOM here. Whereas before we looked at the water extractable proportions. In this case, we looked at the bulk. So we chose a alkaline extraction and followed by lyophilization to concentrate that organic matter down for analysis on FTIR, whereas we looked at absorbance and fluorescence properties on the extracts themselves. And so one of the interesting things here, and you can clearly see the aquifer clay, if you look at the NOH extracts, the aquifer clay, aquifer sand, the silt layer, and the riverbank sands all have pretty different colors. And the humic matter, so when you're looking at kind of humic extracts, typically associated with that darker brown color. So it matches up with the water extractable properties too. So very humic-like properties in that clay and silt layer. And so here's kind of a representative spectra, FTIR spectra of these samples, whereas a lot of it looks the same. We also measured an aldrich humic acid as a standard and identifying each of the peaks, comparing it to previously measured aldrich HA humic acid standards for NMR or FTR. We had a very good match with the standard after identifying these peaks, and particularly useful for organic matters analysis. This FTR is really sensitive to these carbon and oxygen bonds as well, and hydrogen bonds. And so we used many previous studies to compare this, including those using soil extracts using alkaline solution. Of course, looking for co-occurring confirming signals. So for example, aliphatic CH chains, they will vibrate at, the higher range around 2900, but also the deformation of it will occur at around 1450. So for example, you can have these confirming signals. And this is just, I didn't want to spend much time here, but showing that the top is what we showed before, which is kind of a compressed spectra, whereas the bottom kind of shows the relative absorbance of each of these. And then on the right is kind of the major peaks that were identified. And of course, we wanted to take into account using an alkaline solution will cause some changes. For example, deprotonation of carboxylates. So we considered those as well in the analysis. Okay, and so this is kind of looking at the relative proportions of the major identified functional groups in these sediments. And so we have the carbohydrates in red, aliphatic CH chains in orange, carbonyl groups, yellow, carboxyl green, aromatic carboxylates in blue, and aromatic rings themselves in purple. And so the major thing here is, for example, the silt and clay have a much higher content of sedimentary organic matter than the riverbank sands and the aquifer sands. And so almost 20%, I think roughly 17% of the silt was these carbohydrate groups, whereas for the aquifer silt or the clay, almost none of that was. And so a lot of the previous studies looked at these fine grain layers and knew that they were mobilizing arsenic somehow, whether it was compaction of the clay and then release of organic matter and arsenic, or whether it was feeling it through organic carbon. It seems that minor variations in the relative proportions of these functional groups may, in fact, contribute to arsenic mobilization differently in these fine grained sediments. And so using absorbance fluorescence data too, these kind of matched up very well with our FTIR analyses. So the aromatic functional groups that we identified, I think there was like a 0.92 R squared between the absorbance 254, for example, which is a proxy in the absorbance fluorescence data for aromatic functional groups, whereas carbohydrates and carbonyl from the FTR, those match up pretty well with the freshness and biologic indices of the absorbance and fluorescence data. So kind of another degree of confirmation there. And I'm not showing it here, but we have done a parafact model of this too, using all the samples that we analyzed from the Magna riverbank. So water extracts, river water, groundwater, alkaline extracts. And this is, I just kind of like to compare them. So on the top's the total organic SOM properties, and on the bottom's the water soluble. So kind of two different extractions, two different components of this organic matter, but they seem to match up pretty well. So bringing that all together, I wanted to point out this slide's actually from Juan's data, the PhD student from Texas A&M, and I just thought it was really cool. He had done an electron budget balance, and also looking at the DIC and DOC concentrations where this oxidation of DOC produces DIC. He found that even the oxidation of the dissolved organic carbon wasn't enough to account for the production of dissolved inorganic carbon, which probably implicates another source of this organic carbon in the riverbank, which is likely the sediments. So somehow these sediments are contributing to the observed production of DIC. So it kind of helps, because I know I'm only showing the sediments, so kind of comparing the water chemistry at some points will help. And so the conclusions we kind of drew from this is that if these processes are going to contribute to the mobility of arsenic in the sediments, this silt layer being highly labile, a little bit more biologically active, will act as an electron donor to kind of fuel the microbial-mediated reduction of iron oxides, whether that's in the riverbank sands or the aquifer below, if that is able to contribute to these processes. Whereas in the aquifer, these aromatic carboxylates easily form complexes, and in fact, they're known for maintaining such metals as iron in solution. So if anything, similar to the sodium that we found in chapter 2, these will kind of promote complexation in the aquifer, maintaining arsenic and iron in solution. And so that kind of sums up those first 3 chapters. Whereas chapter 5 is an ongoing study. This one hasn't really been completely finished yet. We're in fact just receiving data, continuing to receive data. So this looks at the solid phase partitioning of arsenic within these riverbank sediments. So, you know, what classes of minerals, what phases in the solid phase is arsenic associated with that therefore controls mobility. So kind of partitioning this out. So, and this is important because the mobility of arsenic is largely controlled by its redox state. Previous studies, however, have decoupled iron and arsenic in some cases, meaning that, of course, not all arsenic release or sequestration is associated with iron oxides, but yet they remain to be the most important control on the mobility of arsenic. And so, for example, on the right-hand side, these are 2 different plots. The top one shows hydrous ferric oxide, so ferrihydrite. And I don't know if you guys can see the scale on the left, but it's orders of magnitude higher than the graph below, meaning that it can sequester and therefore release much more arsenic from the solid phase to the dissolved phase than more crystalline structures such as goethite, magnetite, and likely hematite too. So the more amorphous or relatively unstructured these iron oxides are, the higher controls they'll have on either sequestering or mobilizing arsenic. So to kind of look further into this, we have kind of a series of steps a bit. So we looked at the XRF concentrations, diffuse reflectance properties, ferrozine, which allows us, following an HCl leach, which allows us to kind of look at the HCl reducible iron oxide phases. So we get iron 3 and iron 2, the proportions of those. Then we looked at sequential extractions, targeting specific phases of arsenic. So in this case, we looked at outer sphere, which are easily exchangeable, inner sphere phases of arsenic, which are a little bit more involved in the mineral structure, and then organic matter, amorphous iron oxides or aluminum oxides, so amorphous oxides, and then more crystalline oxides. And then finally, a residual phase, which is typically associated with, say, silicate minerals. And so we also have some OSL data, which looks at the relative age dating of the depositional age of the sediments. And then X-ray absorption spectrometry, and that's still ongoing. So we're waiting on that data, but that will provide the coordination environments of arsenic, iron, manganese, and also elemental mapping of those 3 elements along a continuous sediment core. And so here's an example of what we used for the ferrozene sequential extraction, extract diffuse reflectance, 25 samples from 3 cores. The 3 cores encompass the low edge of the river tide, so about 2 meters into the river and 3 meters out of the river. And then 1 sample in the middle of the intertidal zone, which shows a distinct change in color at about 30 centimeters depth. So a distinct change to a more oxidized iron, about 30 centimeters down. And so some of the results, we had an average of 19.2 grams per kilogram of iron. The proportions of iron 3 and iron 2 determined by ferrozene were about 0.58, which a little bit surprising, but it seems like most of that iron in there is present in the oxidized form. Arsenic was still relatively low, similar to the previous studies we've done there, about 7.7 milligrams per kilogram, whereas manganese was about 300. So these results kind of indicate, there's not, any indication of an NRB per se or anything, but the fact that there isn't a transition between more reducing to more oxidizing iron in one of the cores, at least is what interested me. And while this is ongoing, hopefully elucidate a little bit more by some incoming data. And these are the sequential extractions. So these are each of the samples plotted by depth from each of the cores. And so on the left-hand side of each of these, we have the purple, then we'll have so on to the red and the gray. So the outer sphere is purple, inner sphere is blue. And as you move progressively to the right, it becomes more hard to mobilize the arsenic. However, the amorphous iron oxides are the orange and the crystalline iron oxides are the red. And in general, over 80% of the arsenic was associated with 4 phases, the most being associated with amorphous iron oxides at 32%. And then 23% of the arsenic was associated with crystalline oxides, which together about half the arsenic was associated with iron oxides. And although the amounts are small, like a hypothetical situation, if it were to all be released, it would account for quite a lot. So there's been multiple studies, Naring and Hebone, Herring and Kneebone, and then also Van Geen, showing that it's not necessarily always a lot of arsenic in the sediments that's producing high concentrations of arsenic in the groundwater, but this so-called labile proportion of arsenic, or what's able to be mobilized into the groundwater. From the solid phase, it only takes small amounts to mobilize, to kind of generate high concentrations of arsenic in the groundwater. So in this case, I think Van Geen reported an increase of 200 micrograms per liter from only 0.1 milligram per kilogram. So in this case, that would correspond to about 4,800. But of course, there's a lot of competing processes. The arsenic is not likely to be all released from a single phase suddenly, and it will be most likely re-sequestered or incorporated in another phase. But just kind of a mind, you kind of think about it, given the processes that are going on, this could still be important for implications of arsenic mobility. And just briefly showing the iron and manganese. So the sequential extraction, although it targets arsenic, it provides semi-quantitative amounts of iron and manganese as well. And for both of these were both primarily in the residual phase, smaller proportions in the crystalline oxides and residual or amorphous oxides for iron, whereas for manganese, it's mostly residual, and then for some reason, mostly in the outer sphere. So one thing, hopefully when we get synchrotron data back, we'll be able to explain is kind of this environment of manganese, where it's a lot of the inner outer sphere and organic matter near the surface, and then in general, those more labile concentrations decrease as you move down with depth. And so the OSL data, which we got a couple of weeks ago, I found pretty interesting. So because the specific way we had to collect this data, we weren't able to use these same exact sediment cores as those analyses, but we collected samples from a trench we dug on the riverbank right near that transect, about 20 meters from the river. And then we also collected samples about 40 meters from the river at a bit of a higher elevation from a pond wall that was excavated adjacent to the village. And so what was interesting was that pond wall on the village had sediment age of about 420 years. So it was deposited 420 years ago, whereas that of the riverbank, which is closer to the river, had a much older sediment age. So I found this pretty interesting at first, but the Brahmaputra, which is a river in the Bengal Basin, experiences avulsions from its modern day channel kind of to the west of the Meghna River on the other side of Dhaka, the capital, the Madhapur Terrace. Whereas 240 years ago, it used to flow kind of into the Meghna River channel, and it's one of the most sediment-rich rivers, so it has a large sediment load. And so kind of at this point in time, we're thinking that, you know, these sediments were deposited by the Brahmaputra River during its previous occupation, whereas once it divulged, relatively Meghna River channel has been flowing there for the past 250 years, possibly eroding, but still I would consider it relatively stable. And so this is the OSL data, and these two plots are on the left, we have a probability density and a minimum age model, which kind of shows, you know, two statistical techniques used to identify these ages. And if anything, this provides the youngest possible age of the sediments. So if anything, they're older, which to me was surprising given that such an active river could be depositing sediments so frequently, but yet these seem to be much older. And on the right is the OSL signal. So a lot of times these signals are much higher, but since the young age of the Himalayan sediment deposition and the grains themselves, these are actually common for fluvial sediments to have such low OSL signals, especially for those from the Himalayas. So moving on, I think we're still waiting on synchrotron data, but in general, this chapter shows kind of the partitioning of arsenic along each of these 6 phases, whereas the majority of iron and manganese are in residual phases. Yeah, and some of the implications are going to yet to be described fully, but it appears that a lot of the sedimentary arsenic is still important for supporting these high dissolved arsenic concentrations we observe throughout the riverbank and possibly in the aquifer too. It appears to be an erosional riverbank, and yet hopefully a little bit more of these analyses will flesh out this material here. And so that kind of wraps up our studies at the Meghna River. And now we kind of move on to what I started for the Fulbright project along the Hooghly River. And so I'm kind of combine these two chapters because the chapter 6 is a pretty short chapter, a reconnaissance study. And chapter 7, it's all thanks to Juan. He came over on the Kawashi and worked really well and did a wonderful job with that. So present our work along the Hooghly River to kind of provide another exemplar riverbank study. So initially, I established 4 study sites. 2 of them were sand and 2 were those silt along the Hooghly River. And so you see this is Calcutta, just north of that MK site, for some context. And then the furthest north site was in the Nodia district. So I'd kind of provide a little bit of insight on these too. These sandy riverbanks were the 2 northernmost, whereas the silty riverbanks were the 2 southernmost. And I actually took a lot of time finding these sites because I don't know if you can tell from this map, but a lot of that stretches along the river were either erosional riverbanks or had cement covering them. There's so much kind of to protect the banks from moving because it's a pretty populated area. Whereas the Macaulay site was heavily tidally influenced. We noticed a decrease in tides moving up to the Shantipur site, which is SG in this case. And so looking at kind of the design experiment of this, it's pretty similar to chapter 2. Slight differences where we have the X-ray fluorescence and diffuse reflectance measurements. We did one of those DI water incubation experiments, measured for water extractable organic matter properties, cations, anions, concentrations of trace and major elements. And we also did an HCl extraction to kind of look at these iron oxides where we had ferrozine for Fe2 and Fe3, and then of course the ICP-MS for the elements that were reduced or released from that HCl extraction. And so really briefly, this the concentrations of both iron and arsenic increase along the flow path from each of these sites. So as we move down from the sandy sites throughout to the southernmost silt site, we had a constant increase in iron and arsenic. The arsenic here, also at each of the sites, was quite a bit lower than previous studies along the Meghna River, but similar to our study. So between typically a few milligrams per kilogram and about 12. And the diffuse reflectance, again, not much of a surprise. Looking at those sandy sites, they seem to have quite a bit higher iron oxide content and quite a bit more flat reflectance in the silty capped riverbanks. And so it's kind of just compare it in that figure B, that's looking at the total iron compared to the diffuse reflectance. And so typically there's higher arsenic or higher iron concentrations in these finer grained sediments as opposed to the sands. So looking at the kind of two sites specifically, we chose one sandy site and one silt site to focus more on. And so on the left are the sandy and silt cap site with the iron and arsenic concentrations. And the iron concentrations, we also have the HCl extractable iron 2 incorporated in there as well. Whereas relatively low amount was iron 2. Overall, pretty low concentrations, approximately, I think a third of the arsenic was released from HCl extractions. And looking at the dissolved concentrations that Juan was able to do, there was high levels of dissolved oxygen in the river, throughout the riverbank. And then as we got close to the river, at least for iron and arsenic, those concentrations decreased dramatically and suddenly too. And so again, a closer look at kind of the properties of the sediments between these. So in the sand, we had a high association of HCl extractable iron and arsenic, as shown by the bottom graph C, which plots the HCl extractable arsenic on the y-axis and HCl extractable iron on the x-axis. So in the sands, we had R squared of 0.74, whereas there was almost a negligible or minor negative correlation in the silt sediments between those two parameters. So on average, about 27% of the arsenic was total arsenic was HCl extractable. And just to kind of compare these two figures, that PCA bioplot on the right kind of shows the blue circles as the sands and the red circles as these silt sediment, whereas the silt sediment's associated more with these HCl reducible and redox sensitive parameters. Those riverbank samples have higher proportions of iron 3 and a higher diffuse reflectance at 520 nanometers. And so just again, to bring in a little of the water chemistry from Juan, at this site, he showed that there was mostly evaporite weathering and carbonate dissolution, and postulated that the carbonate dissolution likely attenuates acidity from any DOC mineralization. So here again, he did a electron budget to kind of show that DOC was being used to produce DIC, and similarly, not shown here, chlorine-bromine mass ratio also suggested oxidation of organic matter as a player in the riverbank here. And so in the sand riverbank, the saturation indices for these iron oxide minerals such as goethite, ferrihydrite, and especially magnetite were quite high because of the high concentrations of dissolved oxygen. So that kind of supports what we found in the differences between sediment matter. And so this I kind of modified from some of Kwok's work, some of my previous work at these three riverbanks together to show kind of the three distinct riverbank scenarios that we have. So at the Meghna River site, which is the top large one, we have the labile organic matter rich silt layer, which is producing kind of these redox processes driving more or less dissolution of iron oxides to create these increasing arsenic and iron concentrations towards the river. Whereas in the bottom two, we have the sandy riverbank along the Hooghly River, which seems to be associated with more with iron oxides, and given those dissolved arsenic and iron concentrations, dramatic decrease in those dissolved concentrations once we got close to the river. So it seems to be some early signs of what we were initially looking for, whereas the silt riverbank is mostly just preventing any groundwater mixing or any precipitation of iron oxides. So finally, this chapter 8, last research chapter here, it marks a little bit of a change in direction from the previous ones, which have all been in the Bengal Basin. This study is actually a bit higher altitude along a higher energy river. So we wanted to look at kind of nearer to the Himalayan source, the supposed source of these arsenic-bearing sediments, kind of what are the processes along the river, within the riverbank sediments, operating up in these higher energy rivers, and how do they affect kind of the downstream cycling of arsenic? And so in this figure, the Beas River actually is a tributary of the Sutlej River, which flows into the Indus River Valley. So on that figure on the left, that's the white shaded area towards the left, that river basin. And the middle figure kind of shows these arsenic concentrations along the Beas River and Sutlej in the groundwater. So often they're low, but there have been many reports of elevated arsenic along the flow path spontaneously until you get to the Indus River Valley, which has been well associated with higher levels of arsenic in the groundwater. So here's a little bit of the background. So the study site is here, Himachal Pradesh, India, based out of Mandi. So we took 6 sampling sites where we sampled pore water, river water, sediments for experiments. And of course, we measured the conductivity, temperature, pH in the field, preserved these samples for measurement of cations, anions, and elements. And then we took sediment for diffuse reflectance, extractions, water, HCl, and so on, similar to what we've done in the past. So I don't have much time to show all the elements, but for now, arsenic, iron, and manganese, some early work that's been going on. So the pore water shows pretty high specific conductance as compared to the river water. And it's higher than all those. The pore water has higher concentrations of elements and ions, except for calcium and magnesium, which in the river water, it's very much a carbonate water type, which is common given all the limestone in the area. So one of the things, I have these red circles around up and down. So these are, I took all the previous studies I could find for not just arsenic, iron, and manganese, but all the elements that they reported, and compared them to concentrations along the river as the Bias River flows into the Sutlej River in the state of Punjab of India and into the Indus River. And they consistently increase along the flow path. So there's much higher concentrations. In this case, that down circle refers to the Hariki wetlands, which is just north of the confluence of the Bias and Sutlej. So once you kind of get into this lower elevation too, there's much higher concentrations of these redox sensitive elements, or iron, at least these metals, in the river water. And this, we're kind of still working on these organic chemistry of both the water and the water extractable organic matter, and possibly the sediments themselves. We have two outliers right now, which I think we're going to look at further. For the river water, typically we have DOC in river water between 2 and 5 milligrams per liter. In this case, we have above 15 and almost 30 for one of the samples. But the absorbance, 254, which kind of indicates aromatic organic matter, is pretty low in the water extracts. And it's also pretty low in the rivers, whereas the DOC from the water extracts was a little bit higher than we were expecting. So once we get more analyses on these, I think these will help kind of confirm if there's any, if there's heterotrophic processes, or if this is labile organic matter that can fuel these processes, or if they're mostly under these oxygen conditions just being flushed pretty thoroughly until they get deposited in a lower energy environment. And so there's multiple sediment analyses we've done. Of course, the grain size in these, from that picture that I showed, you can see big boulders and stuff. So we found pockets of sand, and the grain size is quite coarse, about 0.5 millimeters in diameter on average. The arsenic is fairly low, 4 milligrams per kilogram. And same thing with the iron oxides, 11.8. So this is about half of what we found at the Meghna River for both of those concentrations. The iron oxides, in this case, seem to be much more crystalline. They have higher proportions of hematite, for example, than goethite. That's the first time we've seen that. So we have less iron, more oxidized, more crystalline. The FTIR also showed indications of kind of more higher proportions of illite, smectite, muscovite, and chlorite. So a little bit less weathered clay minerals than what we found in the basin. XRD kind of backed that up, showed a lot of quartz primarily. And then in this case, we have, on the left-hand side, we have the total iron and total arsenic, HCl extractable iron, HCl extractable iron 2, and then the water extractable, and that's on the logarithmic scale. And same thing for the arsenic below, of course, not arsenic 2, just HCl extractable arsenic and water extractable arsenic. So we have a lot of oxidized iron. In this case, only 10% of the iron was present as iron 2, so fairly well oxidized. However, given the low concentration of iron and arsenic, and that most of it was oxidized, about 55% of the arsenic was HCl extractable. So although these are in lower amounts, there seems to be arsenic well associated with these pretty oxic iron minerals, which, given the premise that from the Himalayas, these rocks, the arsenic bearing minerals in these rocks, these source rocks, is oxidized from sulfide minerals and simultaneously precipitated with iron oxides, that would seem to be the case here. And so just briefly a PCA another to show kind of relationships between the parameters. This kind of shows the difference between the upstream and downstream sediments, whereas actually in the upstream, we had more clay minerals, and that could possibly be due to some siltation practices or siltation from a dam that's present in the area. So to kind of summarize that, we have, I think, preliminary evidence, as the study is still ongoing, that there will be increase in, say, these redox sensitive elements. So the same idea that these are transported down to these basins and accumulate over time, and then the arsenic's released. I think that holds true in general on a larger scale. This iron and arsenic are associated together in the mineral phase. These high flushing rates, coarse grain size, oxic conditions kind of maintain those relationships until they're deposited in a lower energy environment. However, hopefully these organic analyses will help confirm whether or not there's any participation between or this organic matter at this site and the cycling of iron and arsenic. So I can leave this slide up, but this is just some bullet points of each of the three riverbanks. So all the chapters together of the major findings at them. So I think the Meghna River, we kind of set out looking for this natural reactive barrier, but we established a site that had a silty layer kind of 3-4 meters underneath the riverbank that interacts not only with the hydrology at the site, but also kind of fuels like these redox processes, preventing a natural reactive barrier formation. Whereas the Hooghly River, another early on study, we found kind of compared these two different riverbanks, saw that different deposition, different behavior of iron oxides within each riverbank, of course. Whereas the BS River, kind of finding these low concentrations, highly correlated in a small fraction of the iron oxides with arsenic, and kind of looking at whether or not those will kind of affect the downstream cycling of arsenic, and whether or not this kind of increased association is released along the riverbanks, or if it must be deposited in these lower energy settings. So kind of looking at the downstream cycling of iron and arsenic together. And with that, I think we're beyond time for questions. So thank you.
So I guess the next step will be for questions from the audience or discussions from the audience. I'm actually monitoring the chat too, but I would open up. Why don't you have a glass of water? And then there is some snacks and stuff there, so please help yourself, and then I can open up the session for questions from the audience, whoever is there. Peter. I
may have to repeat it.
You may have to repeat it. Yeah.
I think they can answer over speakers.
Go ahead. Okay, so that was a great one. You're like an explorer. So I guess the topic of my question is the overarching topic is like, what is the most dangerous, given that arsenic and iron are kind of like they're traded like stocks on the market or something like that. They have an original mineral form in the Himalayas, and then they get traded between mineral hosts probably many times as they move down through the high energy rivers into low energy floodplains. And so the topic of my question is kind of like, what is the most dangerous intermediate mineral host of arsenic that we should be paying attention to when we're trying to limit the exposure to arsenic in the gardens, floodplains, and delta type environments. And so like specifically my question is, there's so much evidence of high solid phase arsenic in clays, and the studies that show close spatial associations between high dissolved arsenic and sandy aquifers and their proximity to clays. Why does iron oxide arsenic complexes get so much attention in the sort of groundwater geochemistry literature still, when actually it seems like we should probably be paying a lot more attention to clay facilities? And so like what I don't really like feed you the answer or something, but if silts and clays are an important source of arsenic, what do you think the chemical association is with arsenic in those silting clays that leads to its release from the clay that results? And is that it?
Yeah, I think so.
You were just summarize the question.
Okay, so
like at least in one line, so that everybody can hear.
yeah, so I don't know if the Zoom chat can hear, but I think the essence of the question was, what is given that arsenic's so well documented to be associated in silts and clays, what is the primary mineral associations and how is it released from these silts and clays. Yeah. I've thought about this before too, and I think part of it's possibly associated with organic matter, but within as far as like say silt and clay minerals, I think there's plenty of studies looking at say chlorite and biotite. So these silicate minerals that contain arsenic. And for me, it would be the oxidation of these silicates perhaps could release arsenic. Beyond that, I think there's like an association of arsenic within silicate minerals that perhaps it's kind of well sequestered within these minerals. But in general, I think there's been not many, but enough studies looking at these clay minerals like biotite, muscovite, so like Masuda and Charlotte, and some of these studies, and they all seem to indicate that these are important mineral hosts, or at least relevant. We should look at them when it comes to arsenic, being carried down and released from the sediments. But not many studies have looked at them, so I can't really answer how it's released exactly from the sediments. But speculating, I would say biotite and chlorite, these muscovite minerals too, probably play somewhat of an important role. It's just I don't have the exact answer how it's released.
Well, I think if you look at the byproducts of reductive dissolution, reduced dissolved iron, arsenic, and DIC, right? And some of them, that's what you would predict. But you can get all of those dissolved products from plates without any reductive dissolution.
Mhm.
You can get silicates and oxidation of organic carbon by any unconcepted, so it's sort of, I don't know, there's sort of a disconnect from the literature. There's growing focus on the danger of squeezing clays, releasing arsenic. But like you said, there's not a lot of literature on the stuff that Masuda is focused on, which is like the exact chemical association of arsenic within clay minerals like chlorine. So I think you've gotten closer than most people have.
Yeah, I think that's when I started off talking, saying I have more questions than answers. I think that's definitely one of them. Among them, I don't think maybe synchrotron specific studies looking at clay minerals. I mean, typically people request to look at iron oxide arsenic association. But at least arsenic within the clay minerals has probably only been done a handful of times that I've seen. So yeah, I think certainly I think it's increasing relevance to look at weathering and in terms of arsenic mobility in these sediments. I think that's starting to catch on some, but hopefully I contributed something.
So Barney has a question, and I'll come to Kaushik right after that. Quick question for Sugar and you, and Will to consider, but I won't hear after the answer. How do your lab extractions translate to the real world? Translate to a reactive transport model, understanding that is beyond your goal or background. Would kinetics matter? How would your lab extractions translate to the real world? Is the question. Can you put that in a reactive transport model? And in that case, would
kinetics matter? Well, yeah, I would think they would. It feels like to me, looking at all this is just like a snapshot of all these processes, taking the sediments out, then running extractions on them. I think they probably change frequently between these iron oxide phases. So I think, these iron oxide kinetics happen in a matter of minutes, these transformation of phases. So it almost feels we get only a slice of what's going on at one time. And from there, we extrapolate, the process is going on for however many days or years. So that's kind of, I would say the kinetics matter, but at least you have a starting point for a model.
It's a lot of material to get in one sitting.
Sure.
I'll try to ask. I had a few questions, but I can always ask you outside like that.
Yeah.
Doctor. So, all right. So it goes back with the questions that are posed. What kind of experimentation, lab experimentation in a controlled setting you would design to answer those questions that you still are looking? Because it seems like there are a lot of questions that you cannot just get from the observations.
Yeah.
And from the model, you need to support them or probe them even more.
Yeah.
With some experimentation. So what kind of experimentations do you think will help you to answer those questions that you think remain unanswered?
Okay, yeah. So first off, I think maybe if you unmute yourself and bring them to anybody who has a question, maybe the people on Zoom could hear
I will unmute.
if you're on the Zoom call.
Yeah.
I'm just,
Oh,
maybe
yeah,
that, yeah, maybe that will work. But for now, the question was what, in addition, I have questions that are left unanswered.
See, just.
Never mind. Sorry about that. So the question is, what experiments would you do to support or examine those questions that you still have? I think, yeah, so one of them I mentioned is kind of more specific synchrotron studies for these clay minerals binding arrangements with arsenic. So maybe isolating, some of these silt or clay sediments, or even sieving down to the grain size silts and clays to look at those associations and those mineral phases themselves. But also, I think the organic matter, kind of those analyses. One of my big questions is like, this organic matter is associated, trapped in the sediments. So what's keeping it there? It's bound to something, maybe iron, maybe clay minerals with abundant surface area. So maybe targeted, batch experiments using kind of like a sequential extractions for organics. So maybe looking at solvents. So what's released using different organic solvents, what fractions are mobilized there and what quantities, and that will kind of I think help see what's looking at those binding arrangements too. I think some batch experiments as well, because although I kind of extracted it all and looked at it, I'm not sure if it's easily mobilized from the sediment, if microbes can utilize it with its current binding arrangement in the sediment. So I think for me, that's one of my major questions I have left is it actually mobilized? Is it actually, is it locked up in this humic matter fraction? So I think would be the next step to kind of answer those questions for me. I don't know if you had a specific kind of problem, in mind, but I think more will come to me as I'm, everyday thoughts come to me. So I'm sure more will come to me as I look through it again.
Can I ask just a follow-up? Like, it's not a follow-up, it's like a different question. So you went to all these sites.
Yes.
Do you have any idea about like if there's a correlation between the areas of high arsenic pollution and the demographics that is living there? Is there a correlation between that? Or like my question is, are heavily arsenic polluted areas are poor people, or are they living there? Is there a discrepancy that you see? It's not a science.
Yeah. So I think I'm still the only one that can be heard on Zoom. So the question was, is there any correlation between the areas with high arsenic and the population that lives there? Yeah, I mean, that's tough to answer. It seems high arsenic concentrations are really heterogeneous in the groundwater, and that's still one of the things that's yet to be fully explained. But I guess in my experience, these sites are typically rural villages. So, I mean, you could say they're poor, not well off in that sense, but, the people seem, happy for the most part that you're there. I mean, they have their struggles, but I mean, I think the areas that are a bit better off, per se, they have some water systems, or say, favorable community leaders have safe wells, for example, municipal systems. So like bigger cities that we are near, they have city source water, especially in India. So I think that's tough to answer. But in general, I would say like you have a much higher risk of not being able to solve, if you have not clean water or say arsenic contaminated water, if you're not well off. So I think those are the people that are most affected. I say naturally, these are heterogeneous, occur mostly in those areas, but yeah, they're associated with, I would say, kind of poor, not people with not much means to do anything about it. So more or less get stuck with the problem, right? I would say that's the best way I can answer it.
But I think you hit upon it, said it's like urban, rural side.
Uh-huh.
They're basically arsenic.
Yeah.
So that's very urban. That anybody living in rural area, good chance.
Right.
It's an amplifier.
If you want to get this, then there are some questions in the Zoom. Yeah, so no, just go for the, where the photos are coming. Harshad, if you want to ask your question, unmuting yourself. And then I think Alberto has a question.
Oh, yeah, yeah.
Can I go?
Oh, yes, yes. Oh, Alberto, yes, go ahead.
Thank you, Tom. Great presentation. I have a broader impact question. And I wanted to know in the US where arsenic becomes an important contaminant um, and you know yeah. So I guess that basically that's my question.
In the US where arsenic's kind of a problematic contaminant?
Yes, please.
Okay. Yeah, so I think environmentally, there's some like geothermal areas where arsenic's associated. Some basins like Mississippi River Delta, so similar to Bangladesh in that sense. And then even Texas has some problems, but in general, it's actually quite easy to remove, I think, from the water. So in Bangladesh, you can attach a bag of sand to the end of your wellhead and pump it through there, and most of the arsenic's removed just from the oxidized iron sequestering it. But in the US, I think it's not typically a problem with any municipal system. Even household reverse osmosis will handle it effectively. I think the problem where it does occur is even in some parts of Michigan and Indiana, for people who have completely private wells that aren't tested or monitored or filtered themselves. So those households that rely on private wells in those areas that are a little bit higher risk may have some problems with arsenic contamination themselves. So in general, it's mostly private wells, I'd say, for the people at risk of, say, any elements from arsenic in the drinking water.
Okay, great. Thank you so much.
Yeah, thank you.
Harshad has a question on the top. Or Harshad, if you can unmute yourself and ask.
Yeah, sure. Tom, excellent presentation. Thank you.
Thank you.
So the question I have is, one of your results show that sodium was associated with this organic or humic fraction. So we don't typically see that type of relationship, particularly with sodium, if you just look at any water or pore water samples and compare that. Do you think that sodium actually complexed with that humic fraction that you extracted, and that's why you have that correlation? Or basically those are two independent things, that sodium is coming from dissolution of one of the minerals and humic substances are present there, and that's why you see that correlation?
Yeah, so you're talking about the chapter 2 with the water extractable organic matter and sodium plot?
Yes.
Yeah, yeah. So I found that interesting. I'm not quite sure if they were actually associated in the sediment. And again, this wasn't necessarily groundwater. Those plots were water extractable constituents from sediments. So after incubating it, so somehow those were released together. I mean, sodium's a soil dispersant, for example. So if you have like a lot of organic matter and then sodium-rich soil, it actually disperses organic matter, breaks up the sediments. So that was kind of my thinking, that together, for some reason, this sodium helps mobilize DOC. I'm not sure if they were actually correlated or, complexed in the sediments together. I mean, it's not impossible, but that I do not know. But somehow they were both released from the sediments with the water experiment.
Okay, thanks.
Yep.
Janet has a question. Janet, if you want to unmute yourself.
Hi, Tom. Actually, my question is just to see if there have been any other studies done on rivers that receive sediment from older mountain ranges that basically formed in a similar tectonic setting as the Himalaya.
Okay, so kind of older mountain ranges.
Yeah.
Yeah, I think there have been. So a lot of these, for example, the Mississippi River Delta, the problem, not as big of a delta, and the arsenic problem isn't as pronounced, but similar studies and processes and arsenic enrichment in the groundwater there has been observed. And for kind of in between, say that those mountain ranges in the Himalayas, like the Andes Mountains in South America, those foreland basins also have been associated with like high arsenic groundwater. So I'm not sure if there's like an age where the mountains get too old and all the arsenic's used up per se, but it does seem to be a relation between these, younger or mountains being eroded and then those transportation of sediment, these deltas. So I think there is relationship between other mountain ranges.
Okay, yeah, that's what I was curious about is over time, as the range gets older, do we see less arsenic being trapped in these delta basins? So thank you for that.
Yeah, no problem.
Alan, you had a question, if you want to unmute or? Alan Dutton? Maybe you can repeat the question, Tom.
Yeah, so Alan Dutton's question was, did you have time series data on the groundwater EH/pH? If so, do data suggest either temporal change in redox enough to change what mineral phase would be stable, or any spatial shifting of where the mineral stability domains occur? Yeah, I actually don't have time series data on groundwater EH/pH. I'm not sure if we have that from Texas A&M. We do. So Juan has that. As do you want to? So we'll have Juan answer that, our water chemist.
Time series data. We did collect the time series data. We did collect the time series data, but I haven't had a chance to look at the actual time series. But it was a bit chaotic too. So,
Well,
yeah.
it wasn't that chaotic. I mean, so you measured 3 or 4 observations over one tidal cycle, a single tidal cycle.
Yeah, it was
at
like 2 or
50
3.
50 centimeters depth and 1.5 meters depth.
Mhm.
And you observed that all of the major indicators like specific conductance, pH, and ORP were stable over about an 8-hour period, which covers most of a single semi-diurnal tidal period.
It was, I mean,
Right?
it wasn't like not that stable. It was very different.
Okay,
It was very.
all right, we have to talk later.
Yeah, we'll get back to you, Alan. Thanks for the question.
Okay, any question? Yes, go ahead. I have a question about manganese, because I read a couple articles about elevated manganese in the area.
Mhm.
And also, I think broadly in South Asia. And also, so some of our studies of like sediment or even groundwater that in part areas that we see elevated manganese as well. And also a lot of times the manganese and iron also coexist in terms of, I mean, both of them are redox sensitive and manganese minerals are actually very complex. There are 2,000 of different kinds of minerals. Solve the challenge to actually identify those minerals. So I saw one of your study also has elevated manganese. So I don't know if you or maybe other colleagues look closely about regards of manganese and also the mobility of that association.
Sure. Yeah, so the question was specifically about manganese association with iron, arsenic, and the groundwater sediments, if we see any of that. So yeah, I mean, there's been a lot of studies, West Bengal or so on, looking at manganese and arsenic, kind of their co-association, and even following, I think, like the thermodynamic redox ladder, you would have iron reduction, but manganese would be reduced first. So these manganese oxides too can sequester arsenic. That's always been the thought, but this is always something I've looked at, and I mean, haven't seen in the sediments at least any elevated concentrations of manganese. In fact, it behaved pretty isolated between iron and arsenic in general, especially at the Magma River site. So I think the Beas River sediments, as I'm looking at it, they may be the only sediments I've seen so far that show these associations with manganese. But these are sediments specifically, so the groundwater I haven't necessarily looked at, but I don't think there's been any notable correlations, unlike some previous studies even in the area. So at least for the sediments, I'm still looking into that, but I haven't found any similarities between the two, really. But again, these synchrotron studies, these coordination mapping of these elements, that will either confirm or prove whether or not this manganese and arsenic are actually associated.
Hi, Tom.
Hello.
Hi, this is Hatim Sharif. Yeah, very good presentation. Yeah, and very interesting results. But I have a simple question.
Okay.
I think your research, you didn't finish the research on this topic. What, for example, if another student is to continue working on this topic with Dr. Data, what aspect of your research you think holds the most promise for further exploration?
What's the most
What
promising?
aspect of your research
Uh,
had more promise for further exploration, for further research? Like, do you suggest a certain aspect of your research that, for example, another student should explore further?
yeah. So I may be
And
biased.
that will probably bring maybe more interesting results or some solutions. Or
Yeah, yeah, I do think at least my preference to continue would be probably looking at the organic matter. I think there's a lot to be explained there. I think for a long time, it's been chalked up to labile organic matter, promoting the release. But in fact, I think there may be a lot more to it, whether it's retention in sediments or mobilization from, uh, complexation or prevention of even sequestration because it's complex in solution. So, I mean, that's one of the things that I think left me with more questions than answers. And also that was a part of the pivot since COVID occurred. So I kind of pivoted and discovered that route. But I think there's a lot of interesting work left to be done with that. And I would, like I said, I may be biased, but if a student came on again, I'd like to see at least a part of the project looking a little bit more in depth into those aspects.
okay, good.
Yeah, thank you.
Any other questions from the Zoom? We have Karth Nordstrom there. I know Dr. Shikri has joined. Van is still there, it seems. Yeah, anybody else from the Zoom, and then we can continue the discussion within the room.
Proceed.
So, pretty much with your study, with your detailed study, you have covered most of the alluvial plains of Indian subcontinent. You had this one portion where you spoke about the sediment color. There's this widely used notion of having a correlation between the sediment color and the arsenic levels. You also had mentioned about the conditions where there might be an exception to the generalized taken for notion. But do you think it still stands for across the whole of the alluvial plain, or do you think it should not since time to get it?
So also for clarification, but I have to repeat it there. So the question was, can the color of the sediments in the aquifer, their association with low arsenic in the groundwater, can that be kind of extrapolated throughout the whole basin as a general assumption? Yeah, and I think it has been. And I think like Proshun better, Proshun, I think he's actually worked with some others and done kind of massive scale studies for apps. You download an app on your phone as like say you're drilling wells or you're a villager and you're drilling a well and you snap photos of the sediment and it spits out a probability of whether or not it's safe, something along those lines. So yeah, I mean, it has been extrapolated throughout the basin, whether or not it's completely accurate. I of course not say completely accurate, but it's one of the most useful and readily available indicators, I think. Yeah.
And Harshad just commented that Mike Baker's study in Murshidabad, West Bengal, found some sites with high arsenic, high manganese, and some sites with high arsenic, low manganese in groundwater. That study did not look at sedimentary concentrations though.
Yeah, so the groundwater, I think that's true. The sediments, I haven't, like I said, the synchrotron will be able to confirm or deny, but I really haven't seen manganese behaving similarly to iron or arsenic. It's just kind of done its own thing, actually. So hopefully the synchrotron will help with that.
Go ahead.
So following up on Bayani's question from about 9 questions ago. If you remember from Will's modeling results, like early modeling results, where along a highly fluctuating sloping riverbank do you have the greatest vertical mixing between the river water and the groundwater? Remember roughly where that?
40 meters,
was that?
40 meters.
But like not so much a metric as just like, can you describe that site? Like, is it the shoreline or the furthest extent of the shoreline at high tide, the shoreline at low tide, the shoreline in between high tide and low tide? Wait, do you remember that? Like qualitatively, you have some like the image in your head.
Like the early model showing the kind of discharge and interaction points, I think it was like at the river's edge and then 40 meters from the river, if I remember correctly. I don't know.
But the river
Right.
goes in.
All right. Yeah, I see.
Somewhere over that intertidal zone is where you have the greatest vertical width of it.
Sure.
So like related to Alani's question, you showed a plot where you said EP4, which I assume means dry point denominator location 4.
Yep.
Which is close to kind of like mid-tide, kind of like dry season shoreline. And it was interesting to me that when you showed the sequential extraction results, that was an anomaly at that site. You had the greatest proportion of mobilizable, easily mobilizable, like absorbed arsenic, or maybe it was iron at that site. And you showed the sequential extraction results. And I was kind of relating that to the predictions of the model, where compared to in the subaqueous riverbank and upper riverbank, it was right in that kind of middle part where the shoreline spends the most time, where Will's model predicts the most vertical mixing, where you had this anomaly, you had this like more absorbed arsenic concentrations. You had more purple and blue on your sequential extraction plot.
For
You didn't have slide numbers, so I couldn't write down where.
yeah, no, I know where it is. There we go. Yeah, so this is this one.
Maybe I see a lot of purple there, and I see TP4, and you know, sometimes outliers are just outliers, and sometimes they're everything. So one is also found some special things about the chemistry and the hydraulic gradients around that location, and here you're showing that there's a higher proportion of outer sphere absorbed arsenic.
Yeah, so this is yeah, and it was kind of the first study, that 40 meters is where we found that. So that first study, I remember when he did the first model, I was excited to see it because that 40 meter was exactly where he showed that upwelling part. And then within this, and this is from the first trip, these sequential extractions are from our most recent trip. So I don't know how much change, it's hard to tell how much will change. Yeah, I think that too, but this one's actually 21 meters. So right in the middle. And that might be where you get the greatest mixing. I'm not sure, but I think the riverbank may have had it slightly changed too from the site. 2020, December 2022. So yeah, this DP2, this is the one where it's like a distinct change suddenly. Remember we pulled out that core and we're taking pictures of it? Pretty much. So yeah, and that's the one that goes from, you know, this is a proportion of iron 3, the total iron from ferrozine. So HCl extractable proportion alone, but you know, this goes from about a quarter in this point, and then up to averaging like 75% iron 3 after that. Yeah, that's the squares. So that DP2, that's this location with the brown sand. So you can see that reflected in the you know, this brown point, which is not as, you know, apparent in this photo, but so DP4 was like 3 meters from the river. So I encountered like the low river, that low river point. I got one on kind of both sides of that. And that's DP4. Yeah, that's the one where everything's like, this is just outside the low edge river tide. That's not the brown sand, but that's the one that has a lot of this inner outer sphere as opposed to the other samples.
Right.
Yeah.
So yeah, I mean, okay, so would you expect that? Like if you have a lot of brown sand, means you have a lot of iron oxide, you would expect to have more outer sphere or like more absorption of arsenic at that location?
I mean, I would expect more hematites and more crystalline iron oxides if it were like orange brown sand. The absorption's getting stuck on that right near the river, so maybe more discharges occurring there. Not exactly sure, but for some reason there's more sorbed arsenic than other sites.
Could be related. Oh, it could be related to minerals.
Right. It's hard to tell just from. So, you know, that sorbed arsenic may be able to be removed there too, as it increases towards the river. This is from 2022?
But both,
Okay,
but also if your sand is marinating itself in higher arsenic, it's going to have higher absorbed arsenic
right.
to correspond to the higher dissolved phase.
Yeah, again, that's the kinetics problem. Like how, if I see this in amorphous iron oxides phase, how quickly does that arsenic, when it's flowing by, how quickly is it able to be absorbed or incorporated with those oxides? And that I'm not entirely sure from this data.
Absorption is
Right.
absorption is governed. Its kinetics are. So you don't want to say absorption is together.
Okay.
Harshad, if you want to unmute yourself and quickly ask the question. Harshad?
Sure, Tom. So, I mean, you have talked about these two scenarios, one with the embedded silt layer and another one like silt capped river bank. So it looks like the silt and clay associated with arsenic, that's something we see quite a bit when it is near the rivers. When you go further south, like in this Sundarbans Delta, that's probably going to be more clay and more silty. But we don't hear a lot of arsenic related issues, or groundwater arsenic concentrations are high in that, like in the actual delta or the Sundarban region a lot. So what is your view on that, even though that area probably has more silty clay minerals in there deposited?
Yeah, this is an interesting question. So I haven't actually thought about this much at all. So those Sundarbans, a lot of mangrove forests, certainly a lot of silt and clay, and salt water too, correct?
Yeah.
Yeah.
Right.
Yeah, I think actually Matthew Dietrich has done something about the suspended silt and clay down there, but I would imagine that the arsenic was still be kind of associated in the finer grain elements. I think that's like the idea of the overall arsenic cycle, you know, as it gets eroded, all the way carried down and even taken off the shelf and then, you know, subducted and pretty much lithified and then melted up into an orogenic event again. So I imagine the arsenic's down there. I just am not sure if the saltwater intrusion or the groundwater properties are somewhat different, preventing, you know, that mobilization. And again, yeah, I guess I'm not entirely sure how to answer that. Maybe there's just not a population where it's not a reported problem either. So, I mean, I don't know if you had an idea or if you were just wondering, but I'm not entirely sure about that scenario.
Yeah, okay, yeah, I mean that's fine. I mean, I'm not sure either, but I was just curious seeing this silt and silt, clay, and arsenic association, and why we don't see a lot of groundwater arsenic in that region down there.
Yeah, I mean, I'd have to think about that and maybe look into it a little bit. But yeah, thank you.
Sure.
Good question.
Okay, thanks, Ron.
Any other questions from the audience, students, anybody?
In local media, there were recently couple of papers came out from English University. I think they have also showed high arsenic concentration even in the coastal area.
Oh, okay.
I think that's whatever they expect actually from high arsenic. That is also applicable for Sundarbans.
Okay. Just in case for those on Zoom, we were just told by Pushali here that there are recent papers from, I think, the Mukherjee group showing actually high arsenic in the sediments and groundwater in the Sundarbans.
Okay, so other questions or comments from anyone actually? I just wanted to acknowledge that Dr. Shiki just arrived. Steve, Goodbread, Hamji, and Peter Navet They are from Texas A&M and Vanderbilt. And Heather is, when Tom started his work, one of the things that Heather herself worked on was an arts institute before. And so that was a great connection for us to even start a lot of work on the ICP-MS in her lab. So thank you, Heather, for that. Yeah. Any questions or any comments? If not, okay, good. So I will have to excuse everybody else, and then the committee will stay back, and you folks will meet after question session.
Do you have anything to say to Zoom?
So we have to disconnect the Zoom.
Yeah.
I think, no, we cannot. I mean, her team is there, so
Oh,
her team is there. So
oh no.
just a recording. Yeah, exactly. So just the recording part.
So stop recording then?